Welcome to the Ontario High School video podcast. It has to do with predicting products of chemical reactions and phases of chemical reactions. So stay tuned. The goal of this video podcast is to enable you to use tools such as your periodic table, your activity series, and solubility rules to predict the products and phases of your chemical reactions, especially those that occur in aqueous solution. Let's start with the simplest reactions to predict, which are decomposition reactions. Now, in a decomposition reaction, you'll recognize it by the fact that you will have just one starting reactant. Instead of having multiple reactants that you'll be combining together or rearranging in some way, you'll have one reactant that you will be decomposing or separating either the elements or simpler compounds out of it. So these are the basics that you have to know for this. Binary compounds, and binary compounds are compounds that are made up of two different elements. Binary compounds decompose to their constituent elements. Metal hydroxides decompose to metal oxides and water vapor. Metal carbonates decompose to metal oxides and carbon dioxide. And finally, metal chlorates decompose to metal chlorides and oxygen. Here are some examples of binary compounds decomposing. Our first is mercury 2 chloride, which is a solid, decomposing to liquid mercury and chlorine gas. And it's very important when you look at the gases of elements that are on the periodic table. All the elemental gases, except for the last group, which are the noble gases, all of the elemental gases will be diatomic. So Cl2 represents chlorine gas. If you had fluorine, nitrogen, oxygen, or hydrogen, those also would be diatomic gases. Our second one here is dinitrogen pentoxide, decomposing to nitrogen and oxygen gases, and again we have the equation balanced as well. Our third one is a binary compound iron 3 oxide, decomposing to iron, metal, and oxygen gas. And then finally we have sulfur hexachloride, decomposing to sulfur, elemental sulfur. And you'll notice here that this form of elemental sulfur that we're looking at is in an octahedral form, meaning it is S8 rather than just S. And so you can see this is a pretty huge number balancing that you don't normally see, coefficient of 24, but in this case you would. Here are some examples of metal hydroxides decomposing. Now, when you see a metal hydroxide decomposing, oftentimes over the arrow there will be a delta sign written showing that it is decomposing because of the addition of heat. So you can see here magnesium hydroxide, solid decomposing to solid magnesium oxide, plus water vapor, H2O, in its gaseous form. The next one we have cobalt 3 hydroxide, decomposing to cobalt oxide and water vapor. We have iron 2 hydroxide decomposing to iron 2 oxide and water vapor. And finally we have sodium hydroxide decomposing to sodium oxide and water vapor. Again, the pattern for metal hydroxides when they decompose is to go to a metal oxide and to water. Here are some examples of metal carbonates decomposing. We have calcium carbonate decomposing to calcium oxide and carbon dioxide, lead 4 carbonate decomposing to lead 4 oxide and carbon dioxide, lithium carbonate decomposing to lithium oxide and carbon dioxide, and then finally iron 3 carbonate decomposing to iron 3 oxide and carbon dioxide. Metal chlorates decompose to metal chlorides and oxygen. So here are 4 examples. We have solid potassium chlorate decomposing to potassium chloride, solid, and oxygen gas. Solid calcium chlorate decomposing to solid calcium chloride and oxygen gas. Solid iron 3 chlorate decomposing to solid iron 3 chloride and oxygen gas. And finally, solid silver chlorate decomposing to solid silver chloride and oxygen gas. Time for you to try some of these predictions on your own. The first one we have here is a decomposition of strontium hydroxide, then copper 2 chlorate, sodium carbonate, and then carbon tetrachloride. So if you will go ahead and write what you think the products are, and be sure to balance the equations and make sure that you put the phases for the reaction as well. And so you can go ahead and pause the podcast, complete that, and when you come back, the next slide will show you the answers. Welcome back. Let's see how you did. Our first, we have a metal hydroxide, strontium hydroxide, decomposing to solid strontium oxide and water vapor. In the second, we have a metal chlorate, copper 2 chlorate, decomposing to copper 2 chloride and oxygen gas. The third is sodium carbonate, decomposing to sodium oxide and carbon dioxide. And the fourth, we have a binary compound, carbon tetrachloride, decomposing to solid carbon and chlorine gas. Next group of reactions we want to look at are synthesis reactions. And in synthesis reactions, we will normally have multiple reactants forming a single product. So here are some basic types. If you have a pair of elements as products, then you'll form a binary compound of the two elements as the product of the reaction. And this one, it's real important to write the correct formula, so you'll want to look at oxidation states that the two elements commonly form. Active metal oxides added to water will form metal hydroxides. Metal oxides added to non-metal oxides will form salts. And again, a salt here represents any ionic compound where you have a cation and anion combined. And then finally, non-metal oxides and water form acids. So let's take a look at the synthesis of some binary compounds. The first one we have is octahedral sulfur, which is a common form of elemental sulfur. Added to 8 oxygens will yield 8 sulfur dioxides. Then we have sodium added to chlorine gas, forming sodium chloride. Next we have the synthesis of iron 2 oxide from elemental iron and oxygen. And then the synthesis of iron 3 oxide from elemental iron and oxygen. Next we have the synthesis of metal hydroxides from the combination of a metal oxide and water. And if you'll notice, this is just the reverse of the decomposition of metal hydroxides. So our first one, we have sodium oxide added to water will yield sodium hydroxide. Calcium oxide added to water will yield calcium hydroxide. Magnesium oxide added to water will yield magnesium hydroxide. And finally, lithium oxide added to water will yield lithium hydroxide. In the previous slide, we saw that the addition of certain metal oxides to water will form metal hydroxides. And at a later point in the course, we'll talk about classification of compounds called basic anhydrides. And that's what metal oxide added to water is, a basic anhydride, because it ends up forming a basic solution because of the presence of the hydroxide ion that it forms. In this next synthesis, we're adding a non-metal oxide to water, and we're going to form an acid. And non-metal oxides, when combined with water that form acids, are also known as acidic anhydrides. So you'll see that term later on in the course. So the synthesis of acids from non-metal oxides in water. First one we're going to look at is the addition of carbon dioxide to water to form carbonic acid. And this is one you're very familiar with because manufacturers of products such as colas, soft drinks, any carbonated beverage, this is what they do, is they add carbon dioxide to the water to form carbonic acid. The other one that we have here is one of the primary components of acid rain, which is sulfur dioxides that are put out, for instance, industrially by the burning of coal, added to water will form sulfurous acid, H2SO3. and that is, like I say, a major environmental concern for us. But these are the synthesis of acids from nonmetal oxides and water. We've seen in the previous slides that the addition of certain metal oxides to water form metal hydroxides. So those metal oxides we would call basic anhydrides. The addition of certain nonmetal oxides to water form acids, and we would call those acidic anhydrides. We want to look at now the synthesis of a salt, and again, a salt being a combination of a metal cation and a nonmetal anion, polyatomic anion in some cases. And so here we have the salt synthesis from the addition of metal and nonmetal oxides together. And the example we have here is calcium oxide, which is our metal oxide, being added to sulfur dioxide, which is a nonmetal oxide, and it results in the formation of calcium sulfite. And calcium sulfite would be in the classification of a salt. Here are some practice problems. What I recommend that you do is stop the podcast, write these reactions down, predict the products, balance the equations, and then when you're ready to check your answers, go ahead and resume the podcast. Welcome back. Let's see how you did. The first reaction, we have two different elements. We have solid magnesium metal being added to chlorine gas. And in a synthesis reaction, when you have two elements that are being reacted together, we're going to form a binary compound. Now, magnesium always has a 2+ oxidation state or charge. It's a group 2 or 2A, Roman numeral 2A element, depending on what your periodic table labels it as. So this would be a 2+ charge. The chlorine in magnesium chloride, the chloride ion is a 1 negative charge, and so we would need 2 chlorides to balance the 2+ charge on the magnesium, so it would form MgCl2. Again, the importance of writing the correct formula cannot be overstated. The next reaction, we have a metal oxide, potassium oxide, being added to water, and so potassium oxide would be a basic anhydride, and the formation of a metal hydroxide is what we would predict here. So we have K2O solid plus H2O liquid will yield 2 KOH, and that would be aqueous. The next one, we have barium oxide solid being added to sulfur dioxide gas. Here we have a metal oxide and a nonmetal oxide, so we're going to form a salt, ionic compound, and the salt that we form here is barium sulfite. And finally, we have another pair of elements being reacted together, aluminum and oxygen, and so we're going to form the compound aluminum oxide. Aluminum always has a 3+ charge when it's in a compound. The oxide ion has a 2 negative charge, so here the formula would be Al2O3, and as we balance this, there would be 4 aluminums for every 3 O2s, yielding 2 Al2O3s.